The last talk of our session and our day before Phil, who will be the penultimate talk, is Dr. Stephen Friend. Stephen is a visiting professor of connected medicine at the University of Oxford, the chairman of SAGE Bionetworks, and president and founder of the charity For You and Me. His breakthrough approach from discovery of the first cancer susceptibility genes in the 1980s at Harvard and MIT have brought him through to the startup he launched, Rosetta Informatics, to his time as SVP at Merck, leading the oncology efforts, to co-founding and leading the charity. From 2015 to 2017, he also was a member of the Health Special Projects team at Apple. The title of his talk is From Complex to Complicated Problems, What Are the Known Unknowns and Unknown Unknowns in Using Wearables to Forecast Symptom Transitions. Welcome.
Thank you, Sangeeta. Thanks to the organizers. A pleasure to be here. Phil Sharp started with a slide that showed 4 prongs and health data and AI. And this talk is going to be focused on the 4th prong about medical and lifestyle data. It's going to look at some new ways to generate data from wearables that I hope will marry well with the genomic analyte data discussed earlier today. So to set the stage for this topic, I think it's helpful to go back and look at some more mature examples about complicated projects. If we go back 30 plus years into the mid-'80s, when Bob Weinberg and the group at the Whitehead and Ted Dryge's team sort of in the right place, right time to be able to be one of the groups cloning out genes responsible for cancer. The thing to remember is that this is sort of a very early phase of the Gartner hype cycle, and there was a sense that a set, so almost like a table of oncogenes and tumor suppressor genes would be identified, and that soon therapies would be lined up with various diagnoses, various tumor types. And what we all know in retrospect, and I'm going to use some of these examples of retrospect of how to look at what's going to happen in wearables, is that, look, we're awash in complexity of the data that's been generated. There are certainly enough genes players out there, but I don't think anyone anticipated how poorly they would be organized, how many puzzle question marks there would be about what gene activations or inactivations would be responsible where, and the sort of the concept of some coherence to that pattern 30 years, okay, not 3 years, 30 years later is still, I think, an example of something that we should keep in mind. Second example is by the 90s. People began to think about doing something that's commonplace now, which is building up sets of knowns to query unknowns, build compendia. And when Tim Hughes and the group sort of started building this up as a toolbox to say, if I have these patterns of knowns, and with those knowns, I can then go and query unknown. What was interesting was there was a sense that this actually was going to be a turnkey type of approach. I think Dana came up to me earlier in the conference and said, in fact, that a good fraction of her thesis came out of projects like this. So put on your hat and recognize that there was a sense that if you could build some large compendium, this would allow you to query the unknowns. But as we saw today, as we see every day, the complexity that's out there has been more awkward than you might expect. And then the third, final example is that by 2000, 2005, groups began to say, wouldn't it be nice if we could use pattern recognition, if we could take some set of genes and how they're expressed in one tissue and use that to query and look for prognosis, to look at subsetting genes. So this is, 17 years ago. And it took 15 years for some examples to come through. This example here is where Oncotype DX and MammaPrint actually took that concept of looking at aggressiveness of breast cancer as a mechanism by which to make decisions on who was going to get therapy or not. And actually, it has entered clinical practice 15 years later. So the point I want to make is that at the time, it's really hard to see how sparse the data is, and the complexity of the system doesn't really become apparent until you, the way we do our current research, until you drill in more. So the main lesson is, so as we do our current medical research, you can see where I'm going to go. As we do our current medical research, we're mostly blind to or in denial about the actual complexity until it surfaces. So the question is, how can we potentially get around this? This is the context then for the following. Around 7 or 8 years ago, the explosion of high-resolution genomic and other types of genotypic data became sort of more apparent. And what was surprising, awkward, was that what was really missing was good phenotypic information. We really lacked high-dimensional data around phenotypes. And so we began to ask questions about what were the tools that could be used to give us better phenotypic information so that we might have a better way of mapping the high-dimensional genomic data onto it. And the question was, since the data that was coming out in the area of all aspects of medicine was coming out of the clinic, was coming out of the doctor's office, only when they were seeing patients by the words that they used. Was there a way to actually take the 5 senses that a clinician uses to assess a patient, and could you make it so that you could, outside the office, start collecting that information? Could you use touch, hearing, sight example, to be able to monitor what was happening to individuals actually by themselves outside the clinic? And could you set up a scenario where participants would be interested in what was happening to them? They'd be willing to give their data, share their data and insights, and how to go about doing that. Since by that time, there are already 1 billion smartphones out there, and by now, there are more than 100 million smart watches. The direction we decided to go was, what could we collect off of such devices? How could you do that? And basically, how could you prevent what Cliff Huddis was talking about, which is, how could you prevent this data that is emanating from all of us all the time? How could you make it so you could capture that and turn that into a way of better understanding the phenotypes? So Sage Bionetworks, funded by DARPA, Robert Wood Johnson, started working on ways to sort of harness this technology, and soon recognized that if there was some standard way by which, freed up from institutions, you could ask people to collect data and they could input it, it could be stored, it had the right privacy, et cetera, it would be helpful. And out of this came a project with Apple called ResearchKit, which has now hundreds of such studies going on, hundreds of thousands of individuals who've been giving data. And just to give you a sense of what that unleashed, I just want to take one of the ones that at Sage we worked on around Parkinson's disease. This is back 2014, 2015, called Empower. I'm showing the key people who were involved in that work. So using the smartphone, using the iPhone, we were in a position to enroll more people than had ever been enrolled in a Parkinson trial. Here's 15,000, about 1/6 of those people had Parkinson's disease. And virtually all of them said, not only would I like my data to be used, but I'm willing for you to share it with other qualified researchers worldwide. two things of note that came out of this. One was we began to have a massive map of inter-individual diversity. So for Parkinson's disease, usually you score someone and say the severity of their disease by putting together a number of assessments that add up to the final score. But if you pull apart and say, I want to just look at ability of someone to tap, or ability of them to walk, their gait speed, or looking at balance, or looking at what's happening to their voice, and you separated those out and you scored those, here's an example of 30 individuals ranked, ordered for ability to tap. What you'll see is almost everyone has an individual trajectory that they're on. It's almost as if the prion-like nature of the disease in their brain is not always coming up from one central stalk, but it's coming about and making its damage and the symptoms in quite different ways. So that type of high-dimensional data showed that. But more interesting, we were able to track longitudinally. So here's 4 months of data of this one individual. And we could look at before and after taking a medication like L-DOPA, what their ability to carry out a particular task was. And what you'll see there is fluctuations, both in terms of how they were before, how they were after therapy. And what was obvious was there were ebbs and flows in chronic diseases that if you talk to any clinician or if you talk to any patient or caregiver, whether it's arthritis or Alzheimer's or other diseases, is a part of what's going on. And that interested us. It's not as if there's some steady slope people were on. And we were interested enough in what was going on that we'd included a question that said, what do you think? Why do you think your disease got better or got worse? And what was interesting was that we had 20,000 some responses. Some people responded multiple times. And what was clear was there were situations that were almost micro changes in what was happening to that person and their daily life that were the things that they noted. So it would be things like, I got a new dog, or my daughter has a new child, or I had to move to a new house. And that concept of the variability, but also that the disease was being influenced by what that person was going through, we think is very important. Since that time, lots of efforts have gone on to just highlight when it comes from taking electrical signals to physiologic signals to clinical signals and sort of going far with that. I think the work going on in Tom Insel and the work at Mindstrong is a nice example. There's some good examples out of MIT that are doing similar things for other diseases. And I think Apple's effort to come up with ways to allow people to recognize that something was happening to them in very large numbers, and how to do that when you have such extreme ratios of those who may not have anything happening to them versus those that actually do are important. What this led us to think about was how close are we, how far are we from being able to do some sort of forecasting of what was going to happen to someone in the next 3 weeks to 3 months. Could we actually what would it take to actually put together a way to be able to say, this is what's going to happen to you if you continue to do this or do that with the way you're carrying out your life. And so behind that, obviously, what then you would like to eventually have is some sort of personal health assistant that allowed you to have some sense of what was happening before the symptom arises or afterwards. We think it's important to have something that actually nurtured you in times of strength instead of taking advantage of you in times of weakness. And also feel strongly that if you're going to build such a structure, that you would like to do it in a way where people are sharing information and support with each other and contributing sort of by each other, for each other, instead of something where someone is doing something to a group. So some community would be needed. The concept of what it would take to do this, pretty straightforward in terms of various devices and capturing information. The heart of the approach that we've taken is redundancy. So along the top are 3 devices listed, the types of signals we can capture off of those. And then for these various symptoms that are shown there, such as mood, the idea is to have those data streams, redundant data streams, coming in that multimodal approach where you have a grounding to truth to be able to get some assessment of what's the way to get signal from it. One of the questions that's out there that we think needs answering is whether the same continuity of compositional layers that allows imaging to be a ripe area to use AI to be able to get some insights from the patterns is going to happen with regard to symptoms. Is it that actually there is a coherence between the micro elements of symptoms and how they basically come together as more integrated symptoms that would allow the way you can put various compositional layers together with some integrity in imaging to actually apply to looking at symptoms. So I'll show you how we're trying to do that. There are a set of unknowns around forecasting so I'd call these known unknowns that we're trying to look at. This concept of binary labels that bin people is a problem in terms of looking at the reality of the complexity. I'll highlight, not all of them, but I'll highlight that the need to incorporate branching of illnesses is going to be key. Almost all the data that you have in medical records of the way clinicians think of progression in disease is linear. We think it's very likely that when you have more high-resolution maps and you can track it, the divergence in the branching patterns will show up, and what you may be able to do is use those branching patterns to say this person is like this person or that. But how do you go and generate the data that would allow you to show the branching patterns? The existing taxonomy of diseases, whether it's multiple sclerosis or Alzheimer's or arthritis, are often a cluster of symptoms that have been put together that aren't necessarily the real ways that those patients are potentially aggregating in a biologic way. So how do you do your ground truth to saying, is this person have X or Y, when in fact those X and Y are as wobbly as they are? And so for that reason, put together a nonprofit foundation, which basically said, let's see if we can look at some of these fundamental questions and put the data, the apps, the algorithms in the public domain for others to try to advance further. So instead of trying to say we're going to solve anything fully, it's more about framing and putting that data where other people can use it. The structure that we've used is one that says we'll get funding in from investors that are interested in a problem, that instead of trying to form an institute or an entity where we're hiring people into it, we'll take individuals who know how to build apps, or they know how to do assessments, or they know how to do the clinical trial, leave them where they are and have those teams come together in a way where the project gets done by everyone being willing to bring the data and their insights together to solve the problem. The example here is one of 8 symptoms that we're working on in pregnancy. To do this work, there are 1,000 individuals who are getting ready to be enrolled in New York to be able to look at, as a feasibility study, what can we do to be able to do the detection and then the forecasting for those symptoms. Pretty straightforward. We take various symptoms for which the signals from the devices that we have we think are most enriched. For these, we're using a phone combined with a Fitbit Versa, an Oura Ring, and a body port for getting the information in. The nice thing there is that women who are pregnant may have started in state A, and during that pregnancy shifted into that symptom and then come back. So we take advantage of all those visits to clinicians to have study nurses collect the ground truth data during those visits, and including one that's 3 months post-delivery. And I won't go through it, but this data comes together, the trajectory clustering and switching state autoregressive model, the types of things that are done by machine learning experts are being done at the Vector Institute for this with Anna Goldenberg and Marzia Gashimi. And that work that was done there in pregnancy has similar work that is being done for a number of other diseases that I mentioned here, where we're looking at what is the impact of lifestyle and stress on the symptom transition that is occurring. Can we detect and forecast those symptom transitions? And there's a project we have on Crohn's disease, looking to see where we can detect the relapse of Crohn's disease. It's going to set up October, November. I'm going to skip through this to go to 3 slides to end. The first is in oncology. We're interested in asking whether the wearables can be a way to build an early detection system for people who are getting brain tumors by taking individuals who have aggressive forms of glioblastoma and basically tracking them through to those that get the tumor, and then retrospectively coming back to look at were there signs that gave us clues that would be sort of an early surveillance. There is a study that we're gearing up to do with the NCI on stress and the effect of getting cancers that takes BRCA1 patients that are at very high risk for going on to get breast cancer and following them with wearables over a 5-year interval to see whether or not there are things that suggest sort of variation in penetrance that will come about. And so I want to end with the fact that wearables at the beginning of this Gartner hype cycle have some powerful opportunities to add phenotypic data that I think could mesh well with genotypic data. Because of those kind of things I started with, I think it's very important that we come up with a set of questions that the community thinks are worth answering in terms of trying to get to some of the principles and ways that things are working, why they're working, instead of just what it is that people have found I'm going to call a wall of questions that I think need to be put in place, that if we had tried to do something like that for some of the genomic work, might have allowed that progress to be a little quicker. Thanks very much.